If you're in business, you probably have a website, but can your site handle your growth? How many visitors before your site slows down or crashes? What about storage and data security? From web hosting to virtual servers, Pair Networks provides the online infrastructure you need to start, grow, and flourish. When it comes to security and updates, don't worry, we've got you covered. Our 24/7 US-based customer support is the best in the industry. No frustrating chatbots or sitting on hold for hours. Check out pair.com today to learn more. That's PAIR.com.
Welcome to the Attention Deficit Disorder Expert Podcast Series by Attitude Magazine.
Hello, everyone. I'm Carol Fleck, and on behalf of the Attitude team, I'm pleased to welcome you to today's ADHD Experts presentation titled Unlocking the Future of ADHD, Advances in Research, Diagnosis, and Treatment. Leading today's presentation is Dr. Peter Jensen. Dr. Jensen founded the REACH Institute in 2006. Its mission is to improve access to mental health care for children by training providers in the diagnosis and treatment of common disorders. Previously, Dr. Jensen was an associate director of child and adolescent research at the National Institutes of Mental Health and the founding director of the Center for the Advancement of Children's Mental Health at Columbia University. In today's webinar, Dr. Jensen will discuss the developments that have improved our understanding of ADHD. We now know that ADHD is a lifelong condition and not solely a childhood disorder as once thought. With scientific advances that help us learn more about the ADHD brain, it's possible that we could discover many more subtypes of ADHD, leading to precision medicine and therapies. We'd like to begin today's webinar by asking this poll question to our live audience. What do you hope ADHD research uncovers or leads to in the future? Please select your answers and comment in the text box under the video player to tell us more. For answers to common webinar questions about slides, transcripts, and certificates of attendance, click on the FAQ tab of your webinar screen. If you're listening in replay or podcast mode, visit attitudemag.com and search podcast 468 to access the webinar resources. If you support the work we're doing here at Attitude to strengthen the ADHD community, we encourage you to visit attitudemag.com/subscribe and sign up for Attitude Magazine. Our fall issue is hitting doorsteps now. Learn how to land the job you want, and caregivers, check out our special Success at School section. Subscribe today for yourself or to share with a teacher or a loved one who could benefit from greater ADHD understanding. Click on the magazine tab on your screen to learn more. Finally, the sponsor of this webinar is Play Attention. Research conducted at Tufts University School of Medicine demonstrates that Play Attention improves attention, behavior, executive function, and overall school performance. Harnessing cutting-edge NASA-inspired technology, Play Attention offers a sophisticated platform for improving executive function and self-regulation. Through our digital trainer, you can control personalized cognitive exercises just using your mind. Additionally, your program comes complete with a dedicated personal executive function coach who will tailor your plan as you progress. Both home and professional programs are available. Contact us at 828-676-2240 or click the link on screen to schedule your live demo and witness Play Attention in action. Visit www.playattention.com to learn more. Attitude thanks our sponsors for supporting our webinars. Sponsorship has no influence on speaker selection or webinar content. So without further ado, I'm so pleased to welcome Dr. Peter Jensen. Thank you so much for joining us today and leading this discussion.
Thank you, Carolyn. Is my audio coming through well?
Yes, it is.
Good. All right. I want to add one thing to what Carol said about what REACH is doing. We realized, now we started back in 2006 while I was at Columbia University, and what we were trying to do was close the 20-year gap almost 20 years between what the research shows and what your typical clinician is doing. Now, that means research that's happening now may not be actually in common day-to-day practice for 2 decades. We saw that and we thought we have to do something about that. So we've been doing that for making sure that the latest research is in the hands of clinicians now. So parents and families don't have to wait 2 decades to get their kids state-of-the-art care after it's too late. But we realized pretty early on, golly, it's true also for adults. And so not only do we coach primary care providers in the latest science for children and adolescents and what providers can do now, but we've also now taken our trainings to adult providers, family medicine, internal medicine, et cetera, the primary care providers that families most often turn to. So this is actually a great webinar. Now, I'm going to focus on what we know initially here, what debates have been settled, but where is the latest research leading? Where are we going? And that becomes the focus of future advances. What are we going to see in the next 15 to 20 years? And so, we've learned a lot. First of all, we've learned that there is a host of possible etiologies. Now, notice I said possible etiologies. And so there's all kinds of neuroanatomic, neurochemical, genetics findings. We've seen injuries to the brain, clearly, and also environmental risk factors. Now, one of the final common pathways for these factors, we're going to touch on each of those in a little more detail, is what we know about brain function, particularly the prefrontal cortex, kind of up here, I like to signal it, but also deeper brain structures, the amygdala, the basal ganglia. Now, if you look at the neurochemistry, in fact, we know that there are changes in dopamine transmission. There the fight or flight chemistry, norepinephrine and epinephrine, and there's changes in serotonin, the serotonin system. And part of the challenge is, when we do a research study, we can look at groups of people, but we still can't use these general research findings to look at a given individual brain and say, aha, this is what caused your ADHD. Now, that should be shocking, that we can't pin down a cause to a person specifically. And that's going to be the harbinger of where we have to go to break things apart with greater, more in-depth understanding. As Carolyn said at the beginning, precision medicine. How do I know precisely what it is for this person? So yes, we see differences in brain structure and the volume of some of these structures, how they signal, but those are group findings. And if anyone tries to sell you that they have a scan that's going to tell you the cause of your ADHD or a child's ADHD, they're selling you something. And I've actually even approached some people out there who are pretty well known. And I've said, look, you're making claims that are misleading. Look, let's design a study to test your claim. And they've never taken me up on it. Why? Because they're making money hawking kind of the idea that they've got the answer. And it just ain't so. Now, so if you get down to the prefrontal cortex, we know a lot about its circuitry and its wiring. And so, yes, one of the major theories is dopamine signaling. And so we know dopamine is a pay attention neurotransmitter, but actually those projections of the dopamine neurons arise from deeper in the brain. For example, in the basal ganglia, deep down in the middle of the brain. And they signal up to this prefrontal cortex to create interest and excitement in given areas. And if we actually study the neurochemistry, we can see that those nerve endings don't secrete as much dopamine. And not only do they not secrete as much, but when they do secrete dopamine, that pay attention neurotransmitter, it doesn't stay in that space. So remember, as I'm surely know, neurons don't actually touch. They actually release a neurotransmitter, the sending neuron, and it goes to a tiny interchemical space like you see here. And as long as it is in that space, it's going to allow the sending of a message through the next neuron. Now, as I'm going to show you a little later, these are very not complex actual networks because they are so interconnected. And that's partly why it's so difficult to get to cause and effect, because you may think this is a single cause, but in fact, those dopamine neurotransmitter signals are actually, if you will, may send to 1,000 different neurons. So one neuron may connect and have its synapses and then dendritic connections to as many as 1,000 other neurons. And so it's exceedingly complex. Now, so part of the trick of our really getting down to it is to think, how do I isolate the action of that neuron? How do I tell what it is doing or is not doing? Now, here's an example. In this particular study, basically they designed a task that kind of like if you go to the gym and you've got a gym coach and he'll know if you're, say, doing a bench press, if you wiggle your body too much and you're using your back, you're not isolating maybe the muscles that are meant to be exercised. And so we're actually doing workarounds. If we've got weakness in a particular muscle, we use other muscles. We bring them online. Now, that can be useful, but when we're trying to isolate, is a given neuron or a given circuit doing what it's supposed to, we actually have to design very specific tasks that don't allow the recruitment, or at least limit the recruitment of a bunch of other neurons, because now we're not studying the neurons that we're most interested. Now, here's an example of doing something called the Stroop task. I won't go into detail on that, but in this particular task, you actually see what normal people do. They can recruit parts of the brain to accomplish the task. A person with ADHD, that area doesn't light up the way it's supposed to. And so this brain is using workarounds, okay? So less efficient pathways to accomplish the same task. This is exactly the kind of thing that we need to do if in the next generation of neuroimaging studies is that we have to figure out the right task that will isolate the area that's problematic. And then in activities like play attention or others, can we exercise that specific area of the brain just like, we use a muscle? And so we know that's how neural circuits can get stronger by exercising them very specifically. So this is an area of great promise, but we are just still at the very beginning of designing those tasks and then figuring out how does one person recruit a different area of the brain, but how about in another person with ADHD? That's not the case. their brains are different. Just like you go to the gym, one person tries benching and they're using all the right muscles. Another person uses a little bit more of maybe the deltoids or the a muscle surrounding the scapula. They may be recruiting different muscles. Same thing's true for the brain. Now, everybody's gotten excited about genes. Problem with the genes is that there may be as many as 25 or more areas of the human genome that are involved in the final presentation of ADHD. So think about that for a moment. 25 different, with 25 different genes, that means that one person might have these four or five genes. Another person might have another 3 or 6 or 7. And so we think of that as a polygenic condition, many genes. And our most complicated disorders, unlike, say, an illness like Huntington's or sickle cell disease, which we think are probably single genes, all right, single problematic genes, or Fragile X, for example. Not so with ADHD. And so, we got excited about some early genetic studies that seemed to be the DRD4, 7 repeat allele. There were several promising, we call candidate genes. Now, how does that square with this research? Notice this little blue line right here. That's how heritable ADHD is. It's way up there, right with height, more than most of our other disorders. Well, so why can't we just say it's all genetic? The problem is, if you got 25 genes and 4 or 5 in one person and 4 or 5 in another person, those genes can be inherited, but it doesn't tell you which genes are turned on at the time of birth or during the prenatal period or later on. So some genes, for example, might require being exposed to elevated bilirubin to actually have the impact on ADHD. And another person, say an infant, may not have elevated bilirubin, and maybe the genes then are not expressed. And that's probably true of a lot of things. Now, we think of that as a gene-environment interaction. So maybe leaching out of Tupperware, when we microwave Tupperware, that may affect some brains during development and not others. And so that's true of, we think, all of those genes. Now, think for a moment about height. So that's our most genetic one, okay, of these conditions here. All right, your parents are tall, you're likely to be tall too. But think about this for a moment. Think about 400 or 500 years ago. Height was just as genetic, but everybody was about 8 to 15 inches shorter if you go back through the history of kind of our species. So nutrition changed how those genes worked. And maybe even things, additives in our foods. We don't know the whole story. And so it was just as genetic then, but a short person with whatever genes still would have been short, but they would have been taller today. And so we think of that as a gene-environment interaction, meaning those genes show up more in certain environments. And finding those environments can be very tricky. Like if you want to look at the impact of chemicals in the cord blood when a baby's born, you realize there's 150 foreign chemicals in a baby's blood, that comes in through the placenta. 150. And so how do you study if everybody's got it? the impact of that thing. So it becomes very difficult when things become widely present, and it becomes very hard to separate out, say, potential gene environment connections. And so that means we've got to be looking and using more clever methods. And there's a lot to think about, because think about all these non-genetic causes. So we don't think these necessarily cause ADHD, but they certainly predispose to ADHD. And we know these things very clearly from many, many studies that, difficulties with oxygen around the time of birth or fetal distress. We know, for example, that low APGARs are linked to later problems. But if you have low APGARs, that's that little test doctors do at the time of birth to see to give you an overall score of, how pink you are and how quickly you breathe, etc. If you have low APGARs, but you have lots of stresses in the family environment, it's going to be a lot worse. And if you have low APGARs and kind of a modeled kind of later environment, the fetal distress no longer has much of an effect. Or traumatic brain injury, tobacco. Does tobacco affect every fetus? No, we don't know that. We just know it's on average effects. Lead on average effects. Lots of trauma and stresses during childhood kind of stress. Okay, and so we can't say that we know these are true causes, but we do know they're associated with later problems. So if you summarize all of what we know across these areas, from brain imaging to the neurochemistry to the genes, these are all big areas now. So yeah, we know those underlying circuits of the brain that lead up to the prefrontal cortex, they seem to get less blood flow. When you do a task, it looks like they aren't using as much oxygen and drawing as much blood in under normal conditions. So we call that hypoperfusion. It doesn't mean the brain's being damaged. It just that means the signaling systems aren't drawing in as much oxygen or glucose. And the brains are smaller. We know it even affects the cerebellum. And the cerebellum is going to be increasingly an important area. And it's been understudied, generally speaking. And so, yeah, as I showed you, the brain may do little workarounds to try to still get the job done of a given attentional task. So heritability, it's strong, but it's way too many genes for us to say it's this 3 or 4 genes. And then complicating all of that, we've got these multiple gene environment interactions that we are only at the beginning of beginning to tease out. Now, there's some good news here. That you'd say sounds like a lot of bad news. Let's see, I think I just inadvertently skipped a slide. Okay, there we go. All right. So, what do we make of the diagnosis? Now, the diagnosis has been tested across the world. We know the diagnosis is valid in terms of predicting problems. You're more likely to have certain difficulties later on in life as an adult with a vocation, marriage, substance use, maybe not earning as much income. But by way of caution, those are averages. Some people do great and find a way to work with some of those challenges and even turn them into strengths. But we can still say it's a real problem worldwide. Doesn't matter what country you're in. We do know that people do respond to the treatments that have been developed. When we study groups of people, we have the same problems on neuropsych testing or neuroimaging. We can see the genes are genetic factors are critical regardless of what the actual specific genes are. And so however we design the study, we can see evidence of heritability. We can see all kinds of animal studies that are kind of shedding new light. And we do know that if we increase one of the major kind of theories about ADHD is that idea to enhance dopamine signaling or even noradrenergic signaling. And yeah, you can actually begin to show benefits and differences if somebody has the diagnosis. So taking a step back, all right, so we do know there's this changes and, if you will, compared to others, inefficiency of the frontal cortical activity. And this part of the brain its job is to say, stop, pay attention, only do this, ignore kind of the noise out my window, ignore these other random thoughts. I have to concentrate, say, as an adult on the job. Ignore these more interesting things. I have to do this. And so that ability, so it shows up sometimes as someone being easily bored in routine tasks and easily distracted by more interesting stimuli. Now think for a moment, what does that mean, really? Well, that would mean if I can make a stimulus, something that someone has to do, more interesting, I might develop a clever workaround, a way to, how do I make the job more interesting? I have a son with ADHD, and he, we knew from childhood this was an issue, and he began to develop his own clever workarounds. And so now he had some natural abilities in new languages. And so somewhere along the way, he learned Vietnamese, got to be very proud of it and very good at it. And so when he was in college, doing a physics class, which bored him to death, what did he do? He said, I'm going to translate the lectures that's coming into Vietnamese. I'm going to take Vietnamese notes. So we found a way to make it interesting, a little more interesting to him, that kind of used some of his natural strengths. That's what people do when they develop video games and play attention or other things that we know. They find ways to make a stimulus more interesting, and then hopefully through that begin to exercise different parts of the brain. How do we do that? Imagine a teacher giving a lecture on animals. Boring, droning on, poor kids at the back of the classroom. Or it's your supervisor droning on about a list of 5 things to remember, and he is just, or she is maybe the world's most boring person. Well, imagine a lecture instead of a simple lecture about animals, say, what carnivores are like. Imagine at the front of the class, there's a lion in a cage, pacing to and fro. Could you make that lecture on lions a little more interesting? I would think so. So think about what kind of things overcome our boredom naturally. Fear. If I'm really scared I'm going to lose my job, that's why I finally get it done the night before. It's fear. Fear can drive that system. Excitement, joy, amusement. And so great teachers are people that thinking about how do I work with my own ADHD or another person's ADHD. They're thinking not just, they got to focus, they got to pay attention. What do I do to stoke up their attention system? So we do know that we've got 2 neurotransmitters that play key roles, noradrenaline and dopamine, but also now we've got discoveries. Why, when you're anxious, do you finally pay attention when you're anxious? Well, serotonin, acetylcholine, and other neurotransmitters may actually be involved. And we may learn more and more about what is going on in this understudied organ, the cerebellum. And so again, correlational studies only. We don't know true causes at the individual level. And if you look at some of the genes we have identified, it's tiny fractions of people that might apply to, and it's never 1, 2, or 3 genes. It's probably 4 or 5 or 6. And which those 4, 5, or 6 are for a given person, that's kind of an area for the future. We hope we're going to see more progress there. And wouldn't it be cool if I knew the specific genes this person had or the specific pathways that their brain uses to get by? If I knew that, how do I develop a set of exercises like play attention or other things that work not just on average? And you have to say play attention works on average. We don't know how to target the individual, that's what's going to actually be necessary. And so those are some of the challenges for us. Now, the good news in the meantime is we've decided a lot of medications. And all of these have been shown in various controlled studies to actually work more effectively than placebo. The stimulants are across the board, on average, the most effective medicines. But there are some people who have an incredible response to one of these other agents, or they didn't respond or had side effects, or there are other issues. So do these agents work? Yes, for fewer people. And on average, they don't work quite as effectively. But averages don't tell you about the individual person who maybe finally found that was the right medicine. We know a lot about the therapies as well. And so we started back multiple generations ago with using rewards and consequences, teaching parents how to do them, putting them in a classroom. In the last 10 years, we've learned strategies for working with older kids that are better than just anything else. We've got CBT for adults. And so, we've got 3 or 4 different CBT programs that you can teach an adult, actually begin how to do it. And of course, we've now got people trying to get very clever with isolating brain circuits through specific activities like video games. Endeavor is one of the ones approved by the FDA for attention, and biofeedback training. Now, I put a plus minus here. Why did I do that? The field has been littered with claims about the great advances in biofeedback training. Unfortunately, some recent, very cleverly conducted trials where they used sham biofeedback. And so the patients who are doing this, and so think about 10, 20 sessions of biofeedback, can be expensive, showed the sham, the pretend biofeedback, where the patient was responding to the signal and trying to kind of use and relax and focus their brain in a particular way, showed no benefits over the sham, despite the fact there's a lot of people out there selling it. Now, it's not to say it doesn't work for some people, but on average, compared to a good sham or a good placebo, in fact, it hasn't been shown to be better than those shams. So that's where we've come. A lot of advances. We know it's a real condition. It's not caused per se by other things. It isn't just bipolar or personality disorder. And we've got a lot of work with some providers getting them really to understand this is a bona fide condition. We know genes are important. Now what I want to do is turn to thinking about some other ways that we could think about what is ADHD. Now, a current term people are using is neurodiversity. I don't have just autism. I have a different brain. And if the sooner people accept I have a different brain, maybe people can think about developing ways to compensate or help me with, if you're a teacher, my different brain. So I want to talk about where the neuroscience is essentially leading us. So the brain needs experience to develop, but there are some parts of the brain that develop regardless of experience. And so we think of those as strongly inborn and genetic. You could put a child in a black box and parts of their brain are still going to develop. But there's two other kinds of development. Some that are looking, waiting for certain experiences so that they can seize on them. And others, if you don't get the experience, that part of the brain shuts down. Let's talk a bit about that. Think about how that might apply to ADHD and a better, more sophisticated understanding of ADHD. So kind of the first point, there are gene-driven processes. Basically the brain is built from inside out. And shortly after fertilization of the egg and the sperm, it begins to rapidly develop. It starts off as a ball, and then that ball begins to elongate. And it's very interesting. Towards the front of that elongated, if you will, almost like a slug, but it's a little long, flat plate. The front begins to form kind of a circle. And then it begins to hollow itself out. And what happens? The inner lining of that little ball begins to give birth to new cells. And those little cells climb up to the outside layer. And then it happens again. And it happens again. And they keep climbing over each other. It happens 6 times. And that's how the cortex develops. And each time a new neuron is birthed, a new layer, it sends out signals to the neighboring neurons, like a little calling card. Hey, and it says, hey, remember me, we're going to need to do some work together over time. And so it basically sends those signals out, and you have then this 6 layers of brain development, cortical development, all interconnected at multiple of the 6 layers down. It's an amazing process. And it's amazing that it actually goes right. Or you could imagine so many little things, maybe a wrong chemical or a problem with a particular gene may affect that. Okay, so that's that first kind of process we're thinking about. Now, the other one is it's waiting. So those are gene-driven fully, pretty much, but sometimes those neurons are waiting for new experiences. And we think of them as having sensitive periods. And it usually has to take place in a certain period of time. And a good example of that is kind of the areas for language development. And so early on, we're hearing all these sounds. And we can, if we're in a French environment, we can begin to hear French sounds. But if I grow up in an English-speaking environment, eventually I'm going to lose the French connections. And that's why. And so they get pruned back. And I'm going to show you a little graphic on this. They get pruned back because they weren't really used or necessary for that period of development. Another one is what we call a dependent. And a good example is vision. If you're born with cataracts and the doctor doesn't discover it, and you don't get that visual stimulation at critical points, you may lose it. It's kind of, some of our neurons are kind of in a use it or lose it situation. And so think of all that happening. Now, this is what happens in the human brain generally. There are huge numbers of connections or synapses. And so look what happens in the first year of life. Trillions, tens of billions of connections are out there. And all these little things have said, calling card, calling card, calling card. Then they begin to get pruned back. because the environment says, we don't need you anymore. Put your resources here. And so this pruning happens until we get up to maybe about 75 or 80. I'm right at that point now. And if any part of this talk doesn't make sense, I'm pointing to that. All right. All right. So think about that important, but think about another way. Think of people with different genes. One kind of set of genes, another set of genes, a third set of genes, and think about environments that may be not so good, where they're not getting all of the right exposures at the critical time, or maybe an environment that's very enriched. And then you can see, hey, given this genome and set of genes in this environment, you can see that some people might really benefit from a particular type of enriched environment at a certain point of brain development versus others may not. So now this has increasingly been studied, and we see this really good in animal models, but we see it in clinical studies as well. What's the impact of, say, deprivation or enhanced environmental exposures? Here's a study with mice. See the mice here? Now, this is a great environment for a mouse. It's like Disney World, all right? So there's a mouse down here. They're playing, they're interacting. Look at all the different colors, shapes, and sizes. And we've done studies of comparing mice in that kind of environment versus this kind of environment, being raised in a very different environment. And what happens? Well, if you actually look at the neurons, their neuron bodies are bigger. They have more connections if they have that enhanced environment. And not only do they have more connections, they actually have stronger blood flow. And so we see that in the capillaries. And so following, groups of animals, now we can't do this, of those that are in a kind of a standard environment or inhibited, deprived environment or enriched environment, we can begin to see the differences in both how many connections they form. And so in these enriched environments, they're going to form lots of connections per neuron, and they're going to have, again, more connections and better blood flow. So if you apply this to humans, just think about how ADHD might develop. What's in the physical environment? Things that we don't really know. What kind of early exposures? Like, is an iPad a good thing or not? Would it be preferable to sit on a parent's lap and have them read to you? Those are tough studies because you can't randomize. How about possible genetic causes? How about things taking place within the child's inner brain, even as a function of things like additives or other exposures? Now, play that out. How about if it happens early? How does it unfold later? Just think about the complexity of why these things are so hard to study. Okay. Now, if you take that and you think about even at the level of a single neuron, look at this. So what I've modeled here is 8 neurons. Now, we know that each neuron connects to about 1,000 other neurons. This is why it's so much more complicated than even the best computers at this point. And so in terms of the connections, we're talking about 13 times 10 to the 6th. Oh, if I can read that. Yeah, it's 10 to the 6th. If you add in additional connections, because remember, the brain is a correcting system, and it'll give feedback. If you add these feedback loops, we can see the complexity here of the trillions of possible connections we're talking about. And so when we think about you got ADHD, now from the perspective of someone steeped in neuroscience, yeah, that's an okay question. But in fact, it's a silly question. It's okay question because if I know that now, There's things we can do about it. That's so it's an important question. Well, what does that mean, got? What does that mean? You got it. Does it say something that tells us about a huge amount for that individual's underlying brain and course of development? No, it does not. Any more than saying, all right, okay, you got a broken leg, you got a cough. All right, well, we know a lot about, but we always want to go back. Did they get it through a car accident? Do we need to make our cars safer or better airbags or something? We're not at that point with ADHD. And so I always think, be careful. Saying you got it doesn't tell you much about how you got it. It might tell you something about, because of what we know about treatments, what we're going to have to do to intervene with you. But I can only give you 60, 70% bets on whether this treatment's likely to help you. I can't tell you hardly anything at all, whether this medicine is that better than that medicine, or whether this video game is going to actually help you versus the video game plus a medicine plus some other strategies. Maybe finding a better job that's more interesting might be the most useful thing for that person. And so we're still early in this pathway of thinking about causes and consequences. And we need to figure out, is this the child whom we have to really avoid elevated bilirubin? Because they have that gene that bilirubin will activate and greatly increase their risk for ADHD. Or here's a child, too much TV exposure is going to put them greatly at risk if they're using the stimuli like this, bam, 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 bam. And then we ask them to sit in kindergarten. And they went through a wiring period of too much intense video stimulation. Now their brains come to expect that. And we could be in trouble now if we're going to help this child. Because it might have even crossed a critical period. So that means we're going to have to figure out which genes for which person, which imaging studies, which tell us something a little more definitive. We want imaging studies that can tell us where the leg is broken or not. And those aren't guesses anymore. Usually those are pretty good bets. Do we have that yet in our neuroimaging? No, we don't. And so these are the directions we're going to go. For example, I just put a kind of a wish list down here. For example, did you know, we already know, if you have ADHD with some comorbidities, for example, anxiety, you have a very different response that if you have ADHD with, say, conduct problems or ODD, or ADHD with a lot of stormy moodiness. Those are probably different ADHDs if you look at treatment response. Now, we haven't separated that out by genes yet, but that's what we would need to do. Again, looking at specific genes and gene interaction pathways, and I gave you these examples, like how about bilirubin in this child is at a risk, or maternal smoking in this child? All we know is their general risks. And can we then think about how we put different combinations together? Now, I went through the literature and looked at treatments under development that I think are going to be promising. For example, in the adult area, we're now learning for depression, we can stimulate the vagus nerve. And so a little implantable battery pack with electrodes that placed on the back of the head have now been shown to be effective treatments for depression and possibly ADHD. How about TMS? Transcranial magnetic stimulation, these powerful magnets. What they do is they're so powerful they make all the cells and the water molecules line up. So they're in one direction, and then we release the magnet. Guess what? That can temporarily deactivate or change the activity level of some neurons. And so we can target potential neuron areas in the brain to either decrease or increase the activity of relative neurons. Has TMS yet been shown to work for ADHD? No. Has it been shown to work for anxiety and depression? Yes. Are people studying it with ADHD? Yes. Now, again, I wouldn't turn to any of these experimental treatments if I hadn't already tried the proven treatments, like the stimulants, which are about as effective as anything in a pediatric and adult medicine, except for antibiotics that we use to cure infections, have a powerful effect. So actually, I wouldn't use any of these other things until someone had shown they work, and then compared them with stimulants and shown that, these people respond to this and not to stimulants. Again, think of it. Have you shown for whom it works, and how does it compare? So TMS is very promising. Now, the last area I think we're going to see some interesting findings is psychedelic interventions. So MDMA, psilocybin, some of the other roots, both from cactus as well as other plants, have been played with, if you will, for a long time. But there's promising new research saying, the thing that might happen, and we think it might happen, is that a substance like MDMA or LSD opens up the connections temporarily for maybe 2 to 4 days, allowing you new experience if you bring them in to rewire the brain. Could that benefit possibly ADHD? Possibly. Do we have the research? No. Would I go chase this down yet as a new treatment that I need to try? No. I think you'd run a risk there. If you hadn't done every other treatment under the sun, and if then, I'd probably look to one of the universities that's now beginning to do some of these studies, both at Mass General, I saw that Hopkins is doing some of this, and Stanford as well. So it's a brave new world out there. Don't ignore what we know. Don't let stigma or fear of what we know in terms of some of the proven treatments. Can we use stimulants without fear you're going to become addicted? Yes. That's what the data show. In God we trust, but don't believe all this craziness you'll find out there in Scientology and other places. So from everybody, demand data. God will tell you the truth, but we're not talking about that here. We're talking about turning to people who've done good, rigorous science. So let me stop, and we'll take questions. Now, I saw lots of questions coming in.
Yes, we have lots of questions. Thank you, Dr. Jensen. That was so illuminating. Before we start the Q&A, I'd like to thank Play Attention once more for sponsoring this webinar. I'd also like to share the final results from today's poll question. What do you hope ADHD research leads to in the future? Here are the top responses. 15% said more personalized treatment plans. 14% said long-term effects of ADHD and coping strategies. 12% said non-medication interventions. And 11% said improved education approaches. Now to your questions. Dr. Jensen, we had quite a few questions around girls and women who are ignored in research, and women who are diagnosed later in life are an ignored area. Can we expect to see more research on females in general? And can we expect to see research on the impact of hormones on ADHD symptoms from the menstrual cycle and pregnancy through menopause?
Great question. So are we likely? Yeah, one of my dear friends and colleagues is Steve Henshaw And it's worth just studying that name, Stephen, Stephen, Hinshaw, Hinshaw. Now, as consumers, you need to be an active researcher, but don't go generally web searching because you find almost anything. Unless it came from a trusted site like Attention or Chat or ADA, what you get is anyone's guess. Now, you can type in the words PubMed. That will bring you up to an NIH, National Library of Medicine site. And then type in, if you search there's a search place, and you could type in ADHD and the word females. And you're going to get kind of the most recent research on females and ADHD. If you also type in Hinshaw, S, comma, that's going to take you. Now, Steve's been one of the preeminent researchers in the area. That's going to take you. So can you expect more of this? Absolutely. Do hormones affect the brain in females? Absolutely. These are not questions. They're facts. Does it cause ADHD per se? No. But could someone be more irritable, inattentive during kind of the height of the asymptomatic period during the period? Absolutely. We don't think of that as ADHD. We think of that as kind of some temporary dysregulation. But you could still have all of that and have ADHD as well, of course.
We have quite a few questions about ADHD in utero and during pregnancy. So I'll ask the first question. Is there any evidence that certain medications taken during pregnancy can cause ADHD in a child?
We do not have that evidence. So, for example, one of the ones people most commonly worry about is SSRIs. And so if I take an SSRI for, say, maybe depression or anxiety during my pregnancy, am I going to put my child at risk? Now, on the other hand, we do know that if you are taking opioids or heavily abusing stimulants, methamphetamine, cocaine, etc., that does have effect. That can have an effect. But you know what's interesting? Even the best studies of cocaine, heavy cocaine users during pregnancy have been hard-pressed to find much of an effect in babies born where their parents had been heavily using. So it's a different receptor system. We do see opioid effects later on, including morphine, etc. But we have been hard-pressed to see big effects of even heavy use of cocaine. So are there things you should really worry about? Yeah, opioids would be number one on my list, as well as other well-established ones that have been linked to birth defects. But by and large, you just type in birth defects, proven causes, you're going to get a short list.
Okay, another question we had, can ADHD be prevented in utero?
No.
That was quick. Okay.
Short answer. Way too soon to even think about.
Mm-hmm.
We'd have to know the specific causes. Mm-hmm. And are there some kids where something actually, now 40 years from now, will we know that someone has a particular genetic profile, or even 20, and then we could intervene, doing a genetic intervention in utero? That's where the field's going. But ADHD, no, we're talking single gene disorders, not 5 or 10 or 20 gene disorders. We're talking single gene disorders. And if we're going to see that happening, it's most likely to happen in a place with single gene sickle cell. And that's going to precede anything like ADHD by 3 decades.
You talked about birth trauma and the association with ADHD. Is there a higher incidence of babies who are more likely to get ADHD from a vaginal birth versus C-section?
No, but we do know asphyxia. So now if you're having a C-section to prevent fetal distress, if you were to look at, say, situations where the OB delayed, and then you saw a lot of fetal distress before they finally did, or, they just went through vaginal delivery or delayed the C-section. The one I would be worried about is fetal distress that's not quickly responded to and the solution might be C-section. So we just don't see any problems associated with C-sections because usually they're trying to prevent fetal distress or kind of a failure to progress, which eventually will be linked to fetal distress, during pregnancy and delivery.
Okay, this question is about emotional swings from rejection sensitivity. What treatment is helpful for this, and might we one day see this included in the DSM?
So rejection sensitivity is a 30-year-old term. I learned about it back when I was end of my medical student years. So we're talking now 1978 or so. And so it was a prominent idea of a couple interesting therapists. And it describes the idea that someone may be so easy to take offense that kind of those as one of the characteristics, that those persons are always walking on eggshells. Now, in fact, it's not a single diagnosis. We think of it more like a characteristic that might be a part of, say, borderline personality disorder, might be a part of another kind of personality profile. It might be part of when a person's depressed and not when they're not depressed, or when they're anxious, but not when their anxiety disorder is well treated. So rejection sensitivity is a symptom that we always want to look and say, could this be depression? Could this be anxiety? Could this be kind of a long-standing pattern of how personality is developed? Now, do we have specific medications for it? Not really, but we do believe that therapy would be an important thing to work on. And we would be looking, is there depression? Is there anxiety? Having effective treatments for the personality disorders, like say if it was borderline personality disorder, there are some therapies for that as well. And if that's where the rejection sensitivity is coming from, that would be a good place to start.
What do you think about genetic or blood testing and using those results to choose a prescribed medicine?
Oh, great question. All right. So I was at Mayo for 5 years or so, and my dear friend who lived with me actually for a period of time, he became the chair of the department, actually was the first developer, along with Mayo, of these blood tests. Now, what do they do? The things that these blood tests really do is look at the enzymes in the liver, principally, in some parts of some of the blood cells, how they metabolize antidepressants in particular. And so what we know is some people have enzymes that are a different form, same enzyme, but different variant, and they metabolize very quickly, say an antidepressant. Other people have variants of the same general enzymes that metabolize very slowly. Now, what that means is someone who's got, and it could be about 1 in 10 who have very fast enzymes that chew the antidepressant up, it'll mean that they're going to need higher doses of those antidepressants because the normal dose gets chewed right up. If they have the opposite version, they're very slow metabolizers, they're going to be more likely to have higher blood levels with the same doses that doctors might normally use, and they might be more likely to have side effects. Now, those tests are expensive. They do not tell you whether this drug will work and that one won't. They will only tell you if this drug is likely to be slowly metabolized or rapidly metabolized. So we don't recommend them. Even at Mayo, where my friend developed this, we don't recommend them at standard practice. Only if someone has maybe failed 2 or 3, and we can't figure out why. They never respond to the normal doses, or they get side effects so easily. If we see that as a pattern, then we say maybe we need to do this test to figure out which of the antidepressant, and it's really only for antidepressant medications, are they going to be most useful. Now, people are looking at, can we study your genes to see if you respond to a different stimulant, like so for ADHD medicine? It's too soon. We haven't found any proof that these people have a very different response. And so if someone's selling you this test, and you may end up paying $1,000 for it, it's you're throwing good money after bad. It's too soon, and no one can make you that promise yet. So we use it when we're totally puzzled and nothing has worked, and we can't figure out why.
Well, what new information about ADHD has been derived from research, but is not generally being implemented in practice?
Oh, that's a very interesting question. You know, this is should blow you away. The most important finding from research is if you found a medicine that works, your doctor is going to probably prescribe about only half of what's needed, or maybe even a third. And so across the U.S., one of the reasons we developed REACH is doctors way underdose, whether it be for depression or anxiety or ADHD or other difficulties. They usually give about a third of what they need. And so even with my family members, I'm often writing or contacting their providers to say, look, this is what I do. I would recommend to increase. So that's by far the most single problem where people aren't following the research. Who's not following it? It's the doctors, because they're scared. And they're thinking, oh, but maybe he's a substance user. How do I really know? So they don't know how to really do a good interview, follow up with it, ensure compliance, and also how to help you find, say, maybe a good coach or a therapist, because the medications alone would be insufficient. By far, that's our worst problem. And we know from research what the effective doses are. And so I've spent the last almost going on 20 years now trying to teach doctors to do a better job. And I always advise parents, families, consumers, if it's you, look up what the data say for the appropriate dose, the maximum dose. And if you're getting a partial response for the medicine and you're not having side effects or significant problems, the dose should be increased. As a general rule, as long as it's under the levels that have been studied to be safe and effective. By far the biggest problem.
Well, we're going to have to end it there. Dr. Jensen, thank you so much for joining us today and for sharing your expertise with our ADHD community. It's been just really fascinating and educational. Thank you.
Thank you. And I'll be happy to look over the questions. And maybe I can't, obviously there's 1,000 of them, I'm not going to be able to respond. But I'll take a look at what appear to be my top 10, and I'll send it back to Carol.
That would be terrific. And thank you to today's listeners. Make sure you don't miss future Attitude webinars, articles, or research updates by signing up to receive our free email newsletters at attitudemag.com/newsletters. If you're listening in replay or podcast mode, visit attitudemag.com and search podcast 468 to access the webinar resources. If you support the work we're doing here at Attitude to strengthen the ADHD community, we encourage you to visit attitudemag.com/subscribe and sign up for Attitude Magazine. Our fall issue is hitting doorsteps now. Learn how to land the job you want, and caregivers, check out our special Success at School section. Subscribe today for yourself or to share with a teacher or a loved one who could benefit from greater ADHD understanding. Thank you, everyone.
For more Attitude podcasts and information on living well with attention deficit, visit attitudemag.com. That's ADDITUDEMAG.com.
You love podcasts, the stories, the laughs, the unexpected turns. But when this episode ends, the silence starts. Not anymore. Audiobooks.com turns that silence into your next great adventure. With over 450,000 titles, from bestsellers to hidden gems, your love for listening just found its new best friend. And because you already know the joy of audio, we're giving you 3 free audiobooks to start your journey. Imagine your favorite podcast, now with unlimited episodes. That's audiobooks.com. Keep the story going. Sign up for your free trial at audiobooks.com/podcastfree today. Because for podcast lovers like you, the end of an episode is just the beginning. That's audiobooks.com/podcastfree.